going to talk about our Rail AI system and multi-sensor 3D machine vision. The important part, we've talked a lot about geometry. Geometry is great. It tells you there's something wrong. It doesn't really tell you what's wrong, though. So we're trying to look deeper into the track structure, and not just the track itself, but the entire rail corridor infrastructure to take a look and see what could be the problems. And to do that, we need multiple sensors, and we need very accurate geographic data, because not only do we have to have the various sensors pulled together for that trip, but we have to be repeatable in a run-over-run for change detection. There we go. Tetra Tech, a lot of people haven't heard of it. Engineering services and consulting company worldwide. We have 22,000 associates now. It's a little old, 3.1 billion a year. So big company, lots of assets. In the rail space, relatively small group, primarily out of Edmonton up there, and worked with CN. So what we do a lot of, though, is road and runway surveys and asset management. So we started there way back in the 90s. We're asked by a Class 1 railroad, you'll see who it is in a second, to do some work. We did GPR, and we established a new company in 15, started looking at 2D, had a lot of problems with false positives and other issues, went to 3D, had much better success in 15, had a trial car with CN in 2017, and now we have a total of, I think, 10 cars on CN with at least our controller. We don't build the geometry system. There's some of those cars that just have geometry. There are 3 that are all up with what I'm going to show you. And then I'm going to talk about our Tetra Tech car, which is kind of the lessons learned out of all of that, which is the Rail AI car. There it is. You can see dual LiDARs not in the same plane, so they cross-plane and they're resolved in real time on board. Very accurate Planix GPS. Roof is lined with solar cells. So the solar takes care of the car whenever it's in sleep mode, charges the batteries, et cetera, to start it. But we need a diesel to run most of it. There is a geometry beam under it and 2 beams for the 3D sensors as well. It's also provisioned for GPR. This car doesn't have it, but we'll talk about it. That's what it looks like inside. So to your left is the brains of the car. In the back left corner is the geometry rack. In the center is the main brains of the car, the Rail AI controller and systems. There's an air-conditioned system which does air knives over all of the lenses to make sure they stay clean. And there's a large HVAC system, as you can imagine, which is why we can't run all the time on solar, because there's a much bigger power consumption, which is what's on the right. That's the power side. You can see the wells in the back. That's batteries. A little over 2 feet of concrete. Total car weight's 225,000 pounds empty. But in the middle here, we are looking at both sides of the car as a 1,000-gallon diesel tank, and that's a 28 kW diesel generator sitting there on the floor out there. So that's the power. Other things you can look around, there's fire systems, there's security systems, there's a lot of other systems. So this is kind of an overall picture that you can see. I talked about track geometry, GPR, and we've talked to several different providers and have some good options there. And I showed you earlier, we're very familiar with GPR from our road times. There is RailWeb and the 3D TAS systems that we'll talk about. CAR processes all of the data that it takes in real time, or near real time, and then provides defect announcements through the cellular system based on the business rules that the client set up on board. Everything else I think is pretty straightforward. So we'll get into some of the guts of the car. So when it pulls in all this data, it's taking a number of parameters from all of these. So for example, there's 25 parameters that it specifically looks at, assesses, and stores for LiDAR. On fasteners, there's 12 parameters. We're looking at the height of with one of them, we're looking at the height of a spike. With the one that looks at the side, you're looking at which way the spike's leaning. And you can tell from run over run if the spike has changed the lean. Joints, we're looking at the size of the bars, making sure they're right. Comp joints, we look at that as well. All of the bolts, rail head and base mismatch, all those kind of things. All of those are then available in real time. All these sensors are on the one car. So we know, based on, even though we know we're within about a foot normally with the Planix GPS system, but all the other sensors from wherever that is the reference, they all know exactly where they are because you've got the beams, you know the exact distance, you know where you are. So they can all be tied together into real-time composite indices. So you can look at you know, the joint bar looking down, you can look at the gap in the rail measured from the top sensor. You can look at the sides and you can see the bolt patterns, the bar size, all those can be put together in a joint bar indice. So there's a lot of things you can do. They're also run against real-time business rules. So in real time, it will take a look, it'll resolve those two LiDAR point clouds, and it will look at clearances in a tunnel. It will look at sight distances at a grade crossing. It can look at a rolling 39 feet for 12 good ties at class 4 track and alert to those types of things. So that's what having that tight geographic location really gives you. And it, let's see if I can go one more. So what does that do? It brings in a lot of data. So the input is 400 megabytes a second, and the process data is 50. So it ends up with, you know, 1.6 terabytes an hour. Because the car goes into yards, there is something called dwell. There's a 500 terabyte RAID array on the car, and that's enough to store at least 30 days worth of data, which is about how long the fuel tank lasts if you're running hard. So you refuel it, you pop out the drives and put it in, but you get the real time going off the car. So the output is only, excuse me, 1 to 10 megabytes a second that comes off the car. So there's two classes of traffic normally. We could do more. There are the alerts that, hey, you've only got 11 good ties in this 39 feet of track. That can go off an alert with a tight geographic position on that, mile by mile post or by GF. Usually it's both. Excuse me, fighting off a cold. So that goes off. Later on, additional data can go off that either supports those, or the thing that always goes off is our per mile counts of good ties, bad ties, joints in the track, all the inventory stuff goes off at when the car has a comm window that it can do. A lot of times it gets into a yard and it offloads all of that low priority data. So look at the LiDAR real quickly. You can see here, it will identify items like PTC critical items. And like I said, it's within about a foot. So as long as you have your GIS data loaded, you can do PTC monitoring. The green track is the track traveled here. The blue track is the other track. So it can look at, basically a rough gauge. It can look at track center differences, those types of things. Again, I'll try and move along. Tunnel clearances. Here it can identify the slide flints, poles. It will look to see that. We have done it where we go by and we look at, run over run, look at a rock face and detect changes in the rock face or the leaning of trees, those types of things. Drainage ditch, it can look down, the LiDAR can look down, they're mounted high up, and look for geohazards. So here's the track surface analysis, looking down. So it looks at the cross ties and assesses the cross ties, much as the same as the other systems you've seen. Here on the left, you've got an elevation map. Red is close, blue is far away. It's got about a 10-foot width view, so it can see past the ends of the ties, and it can see where you have shy ballast and where it does a ballast assessment to look and see how you're going to do, what your support is from your ballast. On the right, you can see the AI algorithm pointing out issues with the ties. You can also faintly see the plates are identified, the spikes are identified. This view looking down with these 3D lasers has less than a 0.5 millimeter resolution in the vertical and probably less than a meter in the transverse going across. Longitudinal is not as good, so sometimes a little problem with crack and joint bar detection, things like that. But it depends on your speed as to how much, how your repetition's going. And the systems does this at 70 miles an hour. So at track speed, and we can duplex sensors to get that kind of quality up to 140 if Brightline's listening. I know that we're out there. what the system does to look at run over run is it does what we've called tie fingerprinting. So it looks at the patterns of the ties and what their surface and other characteristics are. So it'll look at skew angle and all the different, plate cut different distances. If you know where the top of the tie is and you know how thick a tie plate is, you know what the plate cut is. So it'll look at all these characteristics of the ties and figure out the exact tie by tie number as they're recorded, and will allow you to find that tie again exactly and look at the tie change over time. Concrete ties, again, you know where the top of the concrete tie is, you know where your plate is, so you can figure out your pad thickness. Very, very, less than 0.5 millimeter resolution, so very easy to take a look at some of that. And set in a rule so it can, if it sees a change, something different in the pad thickness or in the seat wear, it can send out an alert and send somebody out to take a look. So here's where we're looking at, looking at asset management of ties. Down to the third, this is actually 75 feet, so 2 39-foot intervals here. But you can see how you're going to have, you'll be able to look at groupings of bad ties. You can look at bad ties per 39 feet, similar to the rolling picture that was done a little previously. So it allows that alarming to come off. It also allows you then to have a good map and look at run over run and see how your ties age and are progressing in real time, or to build a model and age your ties and do tie capital planning. The rail web is, so the first one is 3D TAS, looks down over each rail. Same sensors looking at an oblique angle at both sides of each rail. So it gives you we usually get right now we're getting rail profile off the geometry system, which is where most people are getting that. But what this does is very accurately read the branding stamps on the rail, which lets you then know exactly what that rail started as, so you know what the rail profile should be, and now you know what it is. It also captures every aspect on those on the joint bar and the bolts, tells you how many bolts are in it, and it will tell you the orientation of things. If run over run is moved on a joint bar bolt, it can catch that if you want to catch that. Again, I'm moving along. Feel free to come grab me later on. We can talk. Just don't get too close. I've still got this cough going on. The controller is the heart of the unit. The sensor is a sensor. It's the AI the system uses to identify the objects, and the ability to be able to bring together all of that data and match it and provide very rapid processing to allow for the alerting to send somebody out and go verify the issues. And I think that's about it. Again, I got us ahead so we can get to the adult beverages. Any questions, sir?
How do you take into account repairs or modifications that have been made between runs?
With respect to ties or anything?
Ties particularly.
Well, it would depend how your business rules are set up. In most cases, the business rules are set up to be an issue. So if you've repaired something, it now will be with it. It'll be good. It won't be bad, so it won't alarm. And that will then be it usually retains the previous run in the data bank, so that when it goes back over that same track, it can assess it against the last run. Now, if you're going to go somewhere else, you can pull the drives and start from scratch. But generally, we don't really allow for that, except to be able to compare run over run for some change. So you could build a rule to call out something that was repaired, or you could, and we have not done it, we've talked to railroads about it, put in their track database, things like track disturbance or something. Something happened there, go back and see if you can find that they did some work, something that was there. Anything else? Yeah, Ken.
I missed your quote on what the operating range is.
There's one tank and one diesel. So usually it'll go over 45 days on the diesel, and the data at least a month. So the plan, generally we plan it a month, and you service, you do filters, wipe lenses, and all that, every 30 days, which is what it's been running right now. So So it's been pretty good. And it does have that, it's got that condition air, so the air is conditioned based on, it's got a full weather station. So it knows temperature, humidity, all of that. So those air knives are conditioned so that the air is, lint-free, clean, and it's the right temperature and humidity to blow across them and not cause issues, not cause icing or other things. But it can't, if you're spraying up slush in the Canadian winter, that's a problem. You got to stop it and clean it off, or mud or something. There's, sometimes it's a little too much. Or sand from the FEC. All right. Thanks, everybody.